Welcome to The Explainer. I am incredibly excited to have you here today. Right off the bat, we're going to do something a little different. I want you to step directly into the shoes of a senior network architect. We're going on a deeply visual, under-the-hood journey into the exact logic that powers modern enterprise networks. We are talking about Ethernet LAN switching. By the end of our time together, you won't just know what a switch does on paper, you are literally going to visualize exactly how it thinks.
So let's dive right into this with a real-world mystery. Picture this. You've got a company network and it is crawling to an absolute halt. Users are complaining, applications are dropping left and right. But when you look at your monitoring tools, the physical bandwidth is completely fine. The cables are gigabit, the links are showing us up. So why is the network so heavily congested? Well, the answer to this mystery isn't actually found in the cables at all. It lies hidden deep inside the silicon of your switches, and specifically how they make decisions.
To crack this case, we're going to follow a specific roadmap for this explainer. First up, we'll look at how switches dynamically learn the layout of a network. Second, we're going to uncover the exact step-by-step logic they use to move frames from point A to point B. And finally, we'll look at why networks break. Specifically, we'll uncover the root causes of some truly devastating network loops.
Now, before we can truly appreciate switches, we need to quickly flash back to life without them. Think about legacy Ethernet hubs for a second. A hub operates entirely at the physical layer. Honestly, it's essentially a crowded room where everyone is just shouting at the exact same time. When a hub receives an electrical signal, it blindly repeats that signal out of every single other port. There's no intelligence there, no addressing, just raw, chaotic electrical duplication. A switch, on the other hand, that operates at the data link layer. It acts way more like a highly efficient, intelligent receptionist. It routes private, dedicated calls precisely to the right destination. And this brilliantly illustrates a crucial concept, the collision domain. Because a hub just blindly repeats signals everywhere, all the devices connected to it are trapped in one giant collision domain. If two devices try to talk at once, their signals literally collide and corrupt. Poof, gone. They actually have to rely on a protocol called CCNA/CD, which is essentially an electronic polite cough just to wait their turn. But a switch? A switch carves out every single interface into its own separate collision domain. There is no sharing, no waiting for the whole room to quiet down. It's just pure, dedicated bandwidth for every single connected device. It's a total game changer. Okay, so how does a switch pull off this intelligent routing? Well, it all comes down to identity. Every Ethernet interface on the planet is assigned a MAC address, or a media access control address. This is a 48-bit, universally unique, burned-in hardware address. Think of it as the permanent physical identity of the device. And it is absolutely crucial, because it's the only way the switch knows exactly who is who on the network. So I really want you to try and see the network here. When a computer sends data, it packages it up into an Ethernet frame. And right at the front of this frame is the Ethernet header, which carries two absolutely critical pieces of identity data. First, the source MAC, literally who sent the frame. And second, the destination MAC, who the frame is meant for. The switch looks exclusively at these two specific fields to do its job. Let's literally look inside the switch's memory and see how this all builds out. Think about the MAC address table. When you pull a brand new switch out of the box, or you just freshly rebooted one, this table is completely empty, blank slate. It has absolutely no idea where any devices live. It has to learn everything dynamically from scratch. So how does it actually learn? Let's say we plug in a PC. Let's call him Fred, into port fast Ethernet 0/1. Fred sends a frame. The exact moment that frame enters the switch, the silicon looks at the source MAC address. It thinks, okay, Fred's MAC address just came in on port F0/1. Therefore, Fred must live on port F0/1. And boom, it instantly updates its MAC address table in microseconds. This right here is the first core function, learning. But here is where we hit a really fascinating dilemma. Let's say Fred is trying to talk to his buddy Barney. Fred put Barney's destination MAC address into the frame, but the switch checks its freshly updated table and Barney isn't there yet. The destination is what we call an unknown unicast. So what in the world does the switch do when it has absolutely no idea where the target device lives? Well, it resorts to its second core action, flooding. If the destination is unknown, the switch can't just drop the frame, right? That would break communication. Instead, it creates copies of that frame and floods it out of all active ports, except the port the frame originally came from. It's basically the switch's way of shouting down the hallway, hey, I don't know where you are, so I'm going to send this everywhere and just hope you hear it. And guess what? It totally works. Barney receives the flooded frame and says, "Oh, that's for me," and decides to reply to Fred. When Barney's reply enters the switch on, say, port F0/2, the magic happens all over again. The switch reads Barney's source MAC address and adds it straight into the table. Now, the switch has a map. It knows exactly where Fred is, and it knows exactly where Barney is. So, if we boil all this down, a LAN switch really only has 3 tricks up its sleeve. It only ever does 3 things with a frame. Number 1, it forwards known frames out a single specific port. Number 2, it floods unknown frames or broadcast frames out all ports. And number 3, it filters frames. Let's just take a quick second to clarify that difference between forwarding and filtering, because it is absolutely vital for network efficiency. Forwarding is simple, right? Sending a frame directly to its known destination port. But filtering, that is a brilliant optimization. If a switch looks at a destination MAC and its table says, hey, that device is actually on the exact same port the frame just came in on, the switch simply ignores it. It drops the frame so it doesn't unnecessarily cross the switch's backplane and clog up the rest of the network. All right, let's tie this entire thing together into one solid mental model. PC1 sends a frame to PC3. Step 1, the frame arrives at the switch. Step 2, the switch learns PC1's source MAC. Step 3, PC3 is currently unknown, so the switch floods the frame everywhere. Step 4, PC3 receives it and replies. Step 5, the switch learns PC3's source MAC. And finally, step 6, because both devices are now known and mapped, any future communication between them is simply forwarded out single dedicated ports. That is the complete end-to-end packet journey. Okay, let's bring this abstract logic right back to the physical reality of a data center and jump back to that mystery we started with. Remember? You're staring at the racks. The bandwidth is totally fine, but the network is essentially dead. In the real world, we build networks with redundant physical links between switches, right? We do that so if a cable breaks, the network stays up. But remember how switches behave with unknown frames? Let me ask you something. What happens if a switch gets an unknown unicast or a broadcast frame inside a network that's physically cabled in a circle? Why would the switch's normal, everyday flooding behavior suddenly cause a massive, network-crushing broadcast storm? The culprit? Looping frames. Because switches blindly flood broadcasts, like that all FMAC address or unknown unicasts out all other ports, a frame can go from switch A, down to switch B, over to switch C, and right back up to switch A. And because switches don't alter the frame to track how long it's been alive, that frame will circle endlessly. Literally within fractions of a second, thousands of frames multiply into millions, looping at the speed of light and instantly exhausting every drop of your bandwidth. But it actually gets even worse. This physical loop creates a severely insidious side effect called MAC table instability. Remember, switches learn by looking at the source MAC of incoming frames. If a looping frame from our guy Fred comes in on port 1, the switch learns Fred is on port 1. A microsecond later, that exact same looping frame comes in on port 2. The switch updates, wait, actually Fred is on port 2. The switch's brain essentially melts. It's constantly rewriting its table, which completely breaks its ability to forward legitimate traffic. This whole scenario really hits the nail on the head when it comes to the mindset of a master network engineer. Take it from my own experience. You don't just look at the blinking lights or the physical cables. You have to close your eyes and visualize the invisible logic running inside the silicone. You have to see that MAC address table dynamically updating in real time and mentally trace the path of the frame. So if you take only one thing away from this explainer, make it this foundational mental model. Switches learn exclusively from the source MAC address. Switches make their forwarding decisions based exclusively on the destination MAC address. And when that destination is unknown, or if it's a broadcast, they must flood the frame everywhere to guarantee delivery. Which leaves us with one massive, kind of terrifying question. If having physical loops in our network causes catastrophic broadcast storms and MAC table instability because of flooding, how on earth do we safely build redundant enterprise networks without breaking them? Well, the answer involves teaching our switches to strategically block paths using the spanning tree protocol and segmenting traffic with VLANs. But that is a mystery we will solve in our next explainer. Thank you so much for joining me on this deep dive, and I'll see you in the next one.